Hello everyone, I am Dr. Naresh Kumar, Assistant Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to solve some problems on three-phase induction motor. So first problem here, a three-phase induction motor 26 poles and is connected to 50 Hz AC supply. So now here find out the synchronous speed of the RMF in the motor. So this is the synchronous motor. If you give the three-phase supply, this is AC three-phase supply to this three-phase induction motor, and it will generate the mechanical energy which converts from electrical energy to the mechanical energy. So now here if you give the AC supply to this three-phase in stator of the three-phase induction motor, it will produce the rotating magnetic field, that means RMF, or revolving magnetic field. That revolving magnetic field formula is here. So 120 F by P here. Here F is the supply frequency, F, so 50 Hz supply, and P is the number of poles here. So stator this is having number of poles here 26. Here 120 is a fixed value and P is F is a 50 Hz and 26 is the number of poles. And here this speed, if you calculate this this one, and you will get a value to 231 RPM, rotations per minute, speed units. So now here second question, a three-phase induction motor is wound for 8 poles and supplied from 50 Hz. Same as from this you can find out the this synchronous speed 120 F by P and S equals to, as we discussed in the previous problem, and from this synchronous speed and calculate the slip of the motor when speed is 720 RPM, rotations per minute. So now here solution for this, same thing here. If you give this AC supply 3 phase and 50 Hz AC supply, and this is the induction motor. So here 8 number of poles and 50 Hz. So now here, so synchronous speed here, this one is here 120 F by P, here F equals 50 and number of poles are here 8. So now here 750 RPM. So now here this is the synchronous speed. Synchronous speed is different and running speed is different. So when induction motor rotor speed is, this rotor speed is 720 RPM and this synchronous speed is 750 RPM. So now this is the running speed, motor speed, running speed, NR is 720. And now what about the slip formula? Here that running speed and synchronous speed never be equal. So they are always, there is a difference. So then only motor will rotates and mechanical energy will be developed. So now here slip equals to the difference between synchronous speed and running speed is here, that is slip, and the ratio of this difference in speed and synchronous speed is the percentage slip, and this one is 750 is the NS, this one, and NR is the 720 and this is 750, and that value is 0.04 per unit, this one. And next here if you want the percentage slip equals to into 100, so that value equals to 4%, into 100 means that is 4%. This is the slip 0.04. So now next question. A three-phase 50 Hz three-phase induction motor has 8 poles and operates with a slip of 0.4% at a certain load, and determine the frequency of rotor current. So how you will calculate the rotor current? So see the diagram first. So first I will draw the induction motor diagram, and this is the stator and this one is the rotor. So now here this is the three-phase supply and 50 Hz, and this one is 8 poles. And next here this is the induction motor rotor, and this one is a stator. So now here rotor frequency is different. This is the stator frequency, this is the stator frequency, this is the FS supply frequency, and this rotor frequency is the FR. So these two are different. So transformer is a static device which transfers electrical energy from one circuit to the another circuit, but that supply frequency, that is constant frequency device. It is a variable frequency device. Stator frequency is different and rotor frequency is different. That rotor, this is stator frequency, this one fs, this is 50 Hz. So now, but you need to determine this one. How you will calculate this one? So this fr equals to s into this fs. This is the formula. But this f, we know this 50 Hz, but yes you can calculate. So s value is this one. So now from this you can determine this one. Now here solution for this, fr equals to s into f, that s equals to percentage 0.04, 4% means 0.0 and 58. So 2. So always fs is greater than fr. So a small amount of frequency for rotor frequency of rotor current. So now here a three phase 4-pole induction motor is connected to 50 Hz supply, and voltage induced in the rotor bar conductor is 5 volts. And when rotor is at standstill condition, calculate the voltage and frequency induced in the rotor and rotor conductors at 500 rpm. Here this voltage, so supply voltage, here I am drawing this the diagram. So this is the 3-phase induction motor and this one is a supply. So 3-phase supply. So now here this is 50 Hz supply. This is the rotor and this one is a stator. So stator supply is different and rotor supply is different. So rotor bars are in used here 5 volts and stator voltage is it. So now here if you see the solution first here. So rotor frequency. So already in the previous problem we discussed and this one, and in this problem induced EMF. So this voltage induced in the rotor conductors is V2 dash equals to S into V2. So V2 value, what is the V2 value here? This one. But here in this both, this is a F equals to 50 and this V2 equals to 5. But here we need the slip value. How we will calculate the slip value? So using this formula. But here running speed is here 500 rpm, and but here synchronous speed. How we will calculate the synchronous speed? And synchronous speed equals to 120 f by p. Here 120 into f by p. Here f is this one and this one is this one. 120 f by p, that equals to 1500 rpm. And next slip equals to this 1500 rpm ns minus nr divided by ns, 1500 minus 500 divided by 1500, that equals to 0.67. So now here, so this is the corresponding slip, this one equals 0.67. Now here induced EMF in the rotor conductor equals to V2 dash equals to S into V2. So this V2 equals to 5 and S equals to this one. And same way rotor frequency equals to FR equals to S into FR, that equals to 0.67 into 50 Hz, that equals to 33.5 Hz. A 4-pole 450 Hz 3-phase induction motor running at 1425 rpm. So what will be the frequency of rotor current at speed? So now here what will be the FR equals to S into F. This is supply frequency. Supply frequency is given. But here we need the slip. Slip equals to NR minus NS NS minus NR divided by NS. So NS can be calculated. So NR is given 1425. NS equals to 120 F by P. So same thing here. So if you see the solution, so NS first calculate this one. So NS equals to 120 F by P. So now here 120 F by P. So this one, so 120 into 50 by 4, this one equals to 1500 rpm. So now here, so NR equals to this running speed equals to this one equals to here slip, you need to calculate slip value, or you can substitute in this also. Slip equals to, that equals to NS minus NR divided by 120. So same thing, if you rewrite this equation, NR equals to NS into, this formula is here, slip equals to NS minus NR divided by NS. So that value equals to, So this, if you rewrite this equation, NR equals to NS minus 1S. So or you can write NS is here 1500 minus 1425 divided by 1500, that equals to this slip value equals 0.05. So now here this one. So now here slip, we know this, and you can substitute in this, that F equals to, this is rotor frequency 0.05, and this one, and next thing is this frequency is this one 2.5 Hz. So now supply frequency is always greater than rotor frequency. A 6 poles 50 Hz transformers in a 3-phase induction motor, resistance is 0.03 per phase and standstill resistance of 0.5 per phase. Determine the slip corresponding to the maximum torque and speed of the motor at which torque is developed. So there is a maximum per torque condition here. So that slip at maximum torque condition, slip equals to R2 by R1. So now here the rotor resistance R2 and reactance is X2. So now here that slip equals to 0.06. And next here we have the slip value, this one, and next NR equals to NS minus. So S equals to 1 to NS minus NR divided by S equals to NS minus NR divided by NS. So from this, if you rewrite here, so NR equals NS 1 minus S, that equals here S value is calculated using these two parameters under maximum torque condition. And next thing here, NS can be calculated here. So NS equals to 120 F by P. We know very well this formula, NS equal NS and F by P. So now here 120 F by P. So this is F and P, and this 1000 RPM. And here this value running speed equals to 940 RPM. So now here, so a 8-pole 3-phase 50 Hz induction motor at a at full load slip of 5%, 0.05 slip, and the rotor is star connected, and its per phase resistance and standstill resistance are 0.05 and 0.35 and 2 ohms respectively, and EMF between slip rings is 150 volts. Determine the rotor current per phase and rotor power factor assuming the slip rings are short circuited. Here this one is the EMF between these two, one is this one is 150 volts, and here this E2 equals to this 120 F by P. Now here EL equals to root 3 into V phase, and V phase equals to EL by root 3. So now here this is the line voltage. If you want the phase voltage, that equals to E2 equals to, this is the line voltage, phase rotor phase voltage equals 120 F by P, that equals to 150 by root 3, that equals to 86.61 volts. And now rotor EMF and per phase full load EMF. So now here if you want, this is the slip. So now here for the rotor, this is the EMF. So now here rotor EMF, so that per phase full load, that equals E2 dash equals to S into E2. S value is this one, and this one equals to 86.61, 4.33 volts. And rotor resistance reactance, this is rotor reactance per phase and at full load equals to X2 dash equals to S1. This is the X2 dash 2, and this is 1. And next rotor impedance is this one. Rotor impedance per phase at full load Z2 dash, and this one, and R is fixed. There is no R2 dash equals to not S into R2. So this is, it will not change. So this one is fixed, and this one is S into X2. So now this value is 0.364 ohms. So now here from this rotor current per phase, the E2 dash by Z2. So now here rotor E2 by I equals to V by Z. So now here this is the V and this one is the Z, and 4.33 and the 0.364, that equals to 11.895. And next thing here, So now here a rotor EMF of 3-phase 6-pole 400 Hz 3-phase induction motor alternates 3 Hz, and compute the speed and percentage slip of the induction motor, the rotor copper losses per phase if full load input is 11. So now here this is solution for this one. S equals to, first calculate the slip value. So now this is a rotor frequency and this one is a stator frequency. Fs equals to S into Fr. So now here from this, so this is the Fr and this one is the sub rotor stator frequency. And now here from this you can determine the, so now here 3 by 50 means that is 0.06, that means 6% slip. So now here find out the rotor copper losses. So rotor copper losses here, this one. So now how we will calculate? If so now here first here we need the rotor copper losses. Now here total input power, here total input power equals to, this one equals to this is the input power, this is R2 equals to input power equals to 1119 RPM. So now here first calculate the compute the speed. How we will calculate the speed? N equals to Ns. So first calculate the Ns. So now here NR you need to calculate. So NR you need to calculate first. Slip value we calculate Ns minus NR divided by Ns. So here Ns you calculate. Ns equals to 120 F by P. This is a F and this one is a P. This is the Ns. So now here 120 here Ns is 1000. This is minus NR divided by 1000. That equals to 0.06. So from this NR you calculate that NR value equals to 940. So this one is our speed and percentage slip is over. And so now rotor copper losses. So this is the input. So rotor copper losses equals to S into rotor input. So S means slip. So this is over. Rotor copper losses per phase means that is equals to by 10. And a 400 volts 50 Hz 3-phase induction motor is drawing 50 amperes. And next thing here 50 amperes at a 0.8 power factor, the loss in the motor and stator copper losses is 800 watts and rotor copper losses 800 watts 1800 watts and frictional losses 500 watts and rotor and core losses and 1750 watts, and compute the rotor input power, mechanical power developed and power output powers and efficiency of the motor. This is most important question. So this concept I explained in the efficiency of 3-phase induction motor. So now solution for this one. So first here stator input formula, stator input, how we will calculate that. So these are total losses are given. So total losses are given. These are all losses. So now what type of losses? Stator copper losses, rotor copper losses, frictional losses and rotational loss. So what is the input? So how first calculate the input? So this is the input to the stator. Input to the stator. So that equals to 400. So that equals 400. So VI. So that input to the stator value equals to √3 into VI into cos phi. So cos phi is given, current is given and voltage is given. So now here √3 into V into I into and cos phi, that equals to input equals to this input equals to 27712.8 watts. Now if you give input to the stator of the induction motor, so what will happen? So now there may be a stator input and there may be stator copper losses. So now stator carries the stator is a winding, it carries the current and there may be I square R losses, that stator copper losses. Now remove that stator. If you input stator input minus stator losses means that is rotor input. So minus there may be a stator copper losses, and next thing here stator copper losses. So this is given to the rotor input. So rotor, this is the rotor, this is the stator, this is the rotor. So now here there may be a rotor losses. So now this is the this value equals to 25912. So this value equals to 1800. And next thing here, rotor curve. Next, this is given to the mechanical as final shaft. So now if you, this is the rotor input, this one, and minus rotor copper losses 800, that means 25112. And next thing here this one, rotor output power and mechanical power developed equals to, so that equals to iron losses and frictional losses. And iron losses and frictional losses, if you add this one, so now this minus this one, so there may be a final shaft output here 62.8 watts. That means if you convert into the HP, that equals to horsepower equals to 30.6 HP. Now we know the formula for efficiency equals to percentage efficiency equals to output by input into 100. So this is the final output. This is the rotor input we calculated, mechanical power developed calculated, and this is the efficiency we calculated. Output power we calculated, and this is the efficiency. What is the efficiency of the motor? Efficiency of the motor is output. This is the input. What about the input? Is this one. So this is the input, and this one is the output. So this is the output, and this one is the input. 22,862.8 and 27,712.8. So into 100, output by input into 100 is the efficiency. So now next, a 2200 3-phase 6-pole 50H induction motor is running at 3.5%, and speed of the magnetic field in the revolution, and speed of the rotor. This is the stator and this is the rotor, and speed of the rotor, slip of the rotor, and frequency of rotor. And here we know the formula very well, and this one is a 120 F by P. So stator. So speed of the, so this is a stator and 120 F by P. So 120 F by P. So now here what about the P? 6 pole. This is 6, and this is over this first question. And second question, so speed of the rotor in evolution, rotor speed NR equals to, we know this formula, and slip value is 3.5. So and means in percentage, that means 0.035 percentage, that value. This is a slip, and this one is a synchronous speed. This is in RPM, so 965 rotations per minute. And next, speed of the rotor, percentage, the slip rotor means here N into S. So N into S means S into S, and this one is the NS, and this one is the NR, that is means 35 rotations per minute RPM. And rotor frequency equals to, here you can write this 150 Hz into Fs equals to F into S. This one here you can calculate from this also, or using this one is also. And 0.035 into 50 also, you will get the same value 5. So 1.75 Hz. And next thing here, a 3-phase induction motor runs at 715 rotations per RPM, and at no load at 670 rotations per minute at full load. How many poles does this motor have, and what is the slip at rated load, and what is the speed at 1/4 of rated load, and what is the rotor electrical frequency at 1/4 of load. So this is the solution for this one. And next here, so this is the how many poles here. So poles here how 10 poles. So here the question is how many poles does have to produce. So first here 10 poles. This is the 10 poles here, first question. So this is the question, 120 F by P, 10 poles here. So now here around 10 poles we can expect this one. So 720 here is the synchronous speed. Near to this one is 720, and next here this one is 120 F by P. So this one 70. So here 10 poles. And next thing here, slip value is NS is 720 and this one is a 620. 670. The value is, so here 120 F by P. So directly is given 120 into F value is 60 and this one is P equals to 715. From this, if you calculate it, that value is 10. So after that, this is the slip value, percentage slip value equals to 619 and the motor is operating in the linear regression. So that is 1 by 4th layer. So the slip value equals to 0.25 into 0.0, this one 1 by 4th. So slip 1 by 4th into slip, that equals to 0.174. And resulting that speed equals to substitute in this and 720 here, this one, and that value equals 707. And electrical frequency 1 by 4th equals to this is this frequency, this slip, and this one is the, so 1.04 hertz. A 50 hertz 400 volts 50 hertz 50 kilowatts 2 pole induction motor, a slip of 6% when at full load condition. A full load condition, a friction and windage losses and core losses. The following are the losses. So now here shaft speed and output power and load torque and induced torque and rotor frequency in edges. So now here 120 F by P NS equals to, that equals to this one 120 F by P F, and here 2 pole machine, so that equals to 3000 RPM. And next thing here running speed equals to 1 minus. So this is the slip value 0.06 and this one is this one, and that running speed equals to 2820. And from this here the output power is 50 kilowatts are directly given. And next here, so the torque equals to this P out, this one divided by, so 2 pi F, 2 pi. So now here this is 1 minute by 60 and this one is N value 2 pi N. So now here 169.N Newton meter. And next here power conversion equals to P output plus P friction and windage losses, core losses, and next here P mechanical losses. So this is the output, and this one 520 friction and windage losses, and this one core losses and mechanical losses. So now here 512. So now here 512 is the conversion losses, and this one, and this is same as it is this one 173.3. And next rotor frequency equals to this slip value and 0.06 and this hertz 50 hertz, that value equals to 3 hertz. A 3-phase 60 Hz 2-pole induction motor runs at a no load of 3580 RPM, no load speed RPM. Calculate the slip and electrical frequency of no load full load condition. What is the speed of the regulation? So this is the speed regulation formula. NL minus no speed at no load, speed at full load into 100. So first calculate the speed at no load and speed at full load. So now here, so synchronous speed at no load, so slip value, synchronous speed, and so now here 120 F by P, here slip at no load 3580 and that value is 3000. 120 F by P, if you do this 120 F by P, so that is 3600, that value equals to slip value. So from this you can calculate the frequency value and slip at full load value, this one and this one. This is full load frequency. So now here this is the 358 these two are frequencies, slip and these are frequencies. And next thing, what is the speed regulation? 3580 and 3540 and this one. So this is the speed regulation. I hope all these problems are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you. Thank you very much to you.
Like, share and subscribe. Hit the bell icon for more updates.